Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Science Thursday, we're going to talk about single crystal turbine blade. So let's dive deep into it. So what exactly is the problem that we have to go to crystal, single crystal? Well, problem is that turbine blade loading, basically the high temperature and pressure turbine. Yeah, this puppy is under load, and I mean serious load in two vectors. First, it has to deal with ludicrously high temperature. Second, it has to deal with ludicrously high basically forces also. So what kind of temperature? Well, on a very comfortable chill day, your no load, that's 1000 degrees Celsius, and G force could go as high as 60,000 G. And like I double checked that number. I am hoping that number is wrong, but like way too many places I'm double checking it. It's like even AIs are like, yeah, that's how that 40 to 60,000. I'm like, yeah. Now like how the heck? Well, these things are big. So when you're looking at that, blades could be literally 1 meter in terms of diameter, and they spin at very comfortable, very slow, 2000 RPM when they're idling. And when they're going all out, yeah, 7,000 to 10,000. Some designs are even stupider than that. So fundamentally, that's like minor inconvenience. Now, here's the deal. Why the heck it does not fall apart? Because it's slow. And if you have paid attention to basically jet engines getting started, it does not just like start. It takes its sweet time. So the G-force takes its sweet time to load up. So things can handle it. So it's not like your F1 engine's piston going. It's like it's in one direction. That's the good part. It's a slow ramp up. That's another good part. But again, lot of load, like serious amount of load. And it has to tank this puppy for multiple hours, because you might say, isn't this similar to rocket engine? Yes and no. In terms of rocket engine hot turbine blades, basically things that are after what we call pre-burners, yeah, they are dealing in something similar, but they only have to deal with 8 minutes. This puppy can start with like, you know what, 24 hours. I'm not even joking. Many commercial engines are designed to endure 24 hours of continuous fire. And if you are in military, and God help you if it's a big one which can do mid-air refueling, yeah, at that point in time, we are looking could be 40 hours non-stop. So fundamentally, these things have to tank it. It cannot complain, and it cannot be like, okay, I've landed, you stressed me 2 hours, swap it. No, you have to tank it. So this is brutal. Now, how do we measure it? Because it's a what we classify as flight critical part, and because of the density of these puppies, if anything bad happens and it kaputs, there is no cowling, nothing that can handle it. It's gonna go kaput. It's almost like a uranium pew. So it cannot be contained. So it's a safety critical part, and it generally has like after a certain lifespan, yeet the part. It does not matter whether it's good or not. It does not matter whether we x-ray it or not. Yeet the part after a certain amount. So target is 20,000 hours is starting point, and end goal is 30,000 hours, and we call time between overhauls. So TBO, meaning generally flights have to go through a lot of mild what we call servicing and heavy servicing. So this will be generally done on heavy servicing when you are like, you know, actually going in and like, okay, let's replace part. Generally this will be line item. It's like, okay, now we have fixed the fuel pump, this, okay, turbine blade, yeet all of it. So 30,000 hours is the target, that these things you put it and you do not touch it for 30,000 hours. How much is that? Well, 3.5 years non-stop, 24 into 7 into 365. In flight times, depends on cycling. They also count how much cycling it's going through. Basically, if it's a short haul flight, they might have to replace it quickly. If it's a long haul flight, it could last for much longer. So you have to understand, it's literally handling a flamethrower on its face 24 into 7. So these puppies are problematic to say the least. We went through 3 generations of this technology in order to reach single crystal. So we start with the alloy. So we have a complete different classification, classified as superalloy, because you have to understand, every metal is super strong when you are talking about room temperature, or even 100 degrees Celsius. Like most metal is like, bro, we got this. The moment you cross 200, aluminum is like, I do not got this, I'm out. The moment you cross 300 to 400, even titanium starts to like, bro, yeah, how about this? I can't handle the same stress. Steel, 5 to 600 is like, nah. It's far weaker at 500-600 degrees Celsius versus at like, you know, room temperature or 100 degrees Celsius. Super alloys are like flat line till 800 degrees Celsius. And like it does not care. It's designed to give you maximum strength at 800 degrees Celsius. Meaning we are working our ass off to reduce the creep. What does that mean? That simply means when you have load on a material and you have room temperature, it can handle it. It's like, bro, why we are talking, why we are doing this test is waste of my time. Heat that puppy up. And you do not need to heat it up a lot, like as low as 600 degrees Celsius, it will fail over time. That's what we classify as creep. And be mindful, these turbine blades are under ludicrous G-force continuously for long duration. So 1 hour your turbine is like, I got this. The moment, like, 3 hours it starts to stretch. 4 hours it starts to scrape on the air. 6 hour it cracks. So fundamentally, that's the biggest issue. That's why we have to go to super alloy. Now, super alloys itself, again, I have talked about HIP also, is that if you look at the material, be it super alloy or magical alloy, it does not matter unless the quality control is high. So quality control in this regard is grain boundary. If you do not have good grain boundary control, it's gonna get kaput. So this is how we started. Polycrystalline, you must remember old ancient solar panels. So polycrystalline, but every spot you see, the acid etched it, so it's very visible. All those points are grain boundaries, meaning there is fundamental boundary there. It can crack from there. So it has poor strength. Then by Cold War era, somebody is like, okay, what if we smoked something very good, like quality stuff, like SR-71 quality stuff? It's like, but yeah, bro, blade cannot handle it. It's like, what if we granulized it, meaning the grains going in from one axis? This puppy in G-force direction is like, bro, I do not even care. I do not care. And there is no weakness. There is not a single point where it can crack. It's like, I got this. Again, if some bullet goes into it, that's a different thing. But nothing inherently is weakening it in one axis. It's weak in, like, it can shear, but nothing in one axis. One axis is like, I'm solid. What if we smoked something even better? It's like, what if we had single crystal? Single crystal is like, they're in two axes is exactly the same. It's basically almost as the same grade as what we have for silicon wafer. Single crystal, both axes. It's like, I do not care. Me good. Me got this. So that's why we want ludicrously high quality control in order to have high, even though you can say, oh, all these blades could be made out of same alloy, does not mean all of them will handle the same temperature with same creep. This could have much higher creep. This will have mild creep. This will have no creep. That's the whole point of it. So we want hotter combustion. Physics is like, bro, you want to go hot as possible. Ideally, you want to be as hot as theoretically possible. So let's just say 2,000 to 3,000 degrees Celsius. Yeah, turbine blade is like, nah, calm down, bro, calm down. Turbine blade is like, no. So we started with very low temperature, like 600, 700, because stainless steel was the first puppy that we utilized. Not that good. But once we started to handle nickel, we started to really cook it. Now we are touching like, 1,000 for commercial, and for some big hot puppies like F-22, it could go higher. And I've been told 1,400 is doable, or maybe even higher than that. And I can guarantee you, if somebody figured out an alloy that can handle higher temperature, 5 minutes later, engineers will be like, okay, 3,000 degrees Celsius. You want as hot as possible. Physics likes high heat as much as possible. Again, you want energy from hot to cold. That's how energy flows, and you extract useful energy out of it. If hot is not very hot, it can't flow very quickly. So you want this hot to be not 400 degrees Celsius to 100 degree ambient. You want 100 degree ambient, 3,000 degree fire. Woo. Then you're gonna get maximum power. So even in the same amount of fuel. So that's why you want temperature to be high. And materials are the limiting factor by temperature. Even though this material can handle it, like the super alloys that we utilize, for 800 degrees Celsius, it can give you the full strength. It's like, I got this. Don't worry about me. The moment you go to 900, it's like, start worrying about me. 950 is like, yeah, I'm out. So fundamentally, temperature is the limiting factor. So how do we manage it? I already talked that we have higher than that. It's like, yeah, they generally have cooling holes. So there is in the root, there is a gap. In that gap, you have a gap in the compressor section, like hot compressed air. And yes, relatively hot, meaning ambient, let's just say, is 100 degrees Celsius. The hot air that is coming there, it would be 400 because it's compressed, so it's much hotter. But again, 400 or even 700, some higher designs have 700 degrees Celsius, is still cooler and still below the metal softening point that it can be utilized as a cooling air. And the flame that is falling onto these puppies, those could be as high as 1,500 degrees Celsius or 1,000 plus degrees Celsius. In those sort of scenarios, that air becomes the cooling air. It cools the core of it, then it starts to bleed. It creates what we call film cooling. It creates a buffer layer. It's exactly like how we have Saturn V rocket. If you have seen Saturn V launch, you would have seen the engine, and there will be metal bell, and there will be ugly gas, and then there will be bright yellow gas. It's like, what the hell happened? Well, that ugly gas, that brownish half-burnt gas, is what we call pre-burner exhaust. That is cooler. It's only 700 degrees Celsius. So that is cooler compared to 3,000 degree furnace. So generally you use metal, cool air of 700 degrees, hell. So that's how you protect. Same thing has happened here. So you have cool air of 400 to 700 degrees Celsius, and it creates a buffer layer, a skin layer, and on top of that skin layer you have hell. So that's how it allows the superalloy. And again, if any of the channels failed, like let's just say you got some debris somehow into there, yeah, that blade would be kaput. Like there is no if this then that. Like if that happens, kaput, the blade will be kaput. So it does require cooling. Now, of course, thankfully, these materials are robust enough that they do not fail instantaneously. So even if you're in a flight and something bad happens, it should last long enough for landing. And generally that itself is not high enough for our taste. So we are like, okay, what if we put thermal barrier coating this puppy? Basically, I have no idea, it's like half black magic. This coating allows it to handle upwards of 1000 degrees Celsius, as in like the metal itself without cooling. It can handle like 1000 degrees. Like I got this, fam, 24/7, I got this. So you have that cooling. So we have thermal barrier coating, and then you have internal cooling, which is that internal column of air, and then you have film cooling. All these three things work together to allow us super high mileage. The mileage that we have in our commercial jet right now, if you have showed this or anybody in like at the end of World War II, they're like, what black magic is this? Because again, this turbine says like, I get this. So superalloys. Now, how do we go from superalloy to single crystal? So single crystal is basically relying on the physics fact that whenever you have liquid to solid transition, even in water ice, it always happens, crystallization always happens at a nucleation site. Meaning if you have seen a lot of people who have like, super cooled water bottle and they slam it from the bottom, ice starts to always form up from one place and then it creates a full system. So that is nucleation point. So if you shake it, it creates a nucleation point at the agitation point, and boom, boom, it grows. Now, of course, if you shake it a lot, it will create from multiple sides, but that's how it happens in solid also, as in like a metal also. So when you have molten metal and you solidify it, it will find a nucleation site and then the crystal will grow. If you have a lot of nucleation site, it will create polycrystal. Not a good idea. And if you can guide it, basically you slowly pull it through basically the frozen metal, you can get linear system. This is what we did for SR-71. Now somebody figured out, it's like, is the seed. At the end of the day, these are multiple seeds. You do not want that. You want one seed. If you can control it, basically have one seed that is slowly growing, you're gonna get perfect monocrystal, a single crystal system. So it's all about seed. All you need to do is make sure there is only one seed, and B, it's the condition around it. Basically, conditioning the molten metal is right enough where it does not try to create its own basically nucleation site. It's like, okay, I'm gonna listen to it. Because again, this is a property of metals and materials. They like to listen to them. It's like, oh, there's this one seed. Let me do not worry about it. Let me just align to it. Almost like lazing. It just wants to go with the flow, so to say. So you want to arrange the scenario that is always going into the flow. And in this scenario, we arranged all the flows in one direction. So it gave us very strong blades, but again, in one axis only. And then somebody figured out, what if we had a pigtail into it? Meaning you had a molten metal and you're freezing it. Again, you're going to get a lot of what you call grain boundaries, but you have spiral. Now this spiral is a smooth tail. Now benefit of that is metals do not like turning. Basically grain boundaries itself will collapse if you have to do that, so it collapses. So it's almost like a low pass filter where it's like high noise, only low pass passes here. So then at this root you end up with one seed, and then you slowly grow it. And this is how they are built physically, meaning you have the molten metal and then you slowly pull it out slowly. And generally this is done in vacuum, so you do not have a convection of air that will create a noise and will create a random nucleation site. So you want to make sure like vacuum, and then you slowly pull it down, like very slowly. So all you are doing is basically pigtail is filtering all the basically grain boundaries, only allowing one to pass, and then you slowly control it. And that's the whole point. So cooling has to be controlled. That's why they are done in vacuum, so you can control it. Basically these heating elements are on, they are radiatively heating this puppy. So the molten layer that is on the top does not solidify until the seed crystal reaches it. So and they are cooling it out slowly. And again, the bottom is liquid cooled. So that's how we started the chill plate. That's how we started with what we call columnar crystals, and then we upgraded to single crystal. Basically jump from columnar to single is basically figuring out this pigtail geometry. We did that. And Once you are done, you have something that is robust because it's monocrystal. There is no grain boundary. And again, you might be like, okay, is it only used for turbine blades? No. Any new alloy that comes into the market, how do you know its properties? Well, you generally make this single crystal alloys of it. And once you have that ingot goes into material testing. Then you know, like, this is the upper limit of the material's property. And if you're not getting this, that means the quality control is poor. They're like, isn't that will always be better than what you can get? Yes, but that's the whole point. That's the upper limit. So that's how all materials are tested. And again, that's literally how silicon ingot is. Like, whole IT industry is relying on something like this. Only in silicon generally is done from, because the crucible is huge. It's on the top, the cap is open, then you pull it out. So that's the whole point of single crystal. Basically, you have a liquid, and liquid wants to solidify. Liquid wants to dump its energy. It just wants to align. You're like, hey, don't rush. You're like, chill. We're going to give you the seed. You align yourself to the seed. You give them only one seed, and then you slowly let it grow. And outcome, monocrystal. One monocrystal. And in terms of strength, it's isonomer. It does not care. There is no grain boundary. So this is the whole point of single crystal, generally done in vacuum. Now, what are the limitations of this puppy? Well, it is so complex. Even though it's an ancient technology, like 1970s kind of technology, this puppy is complex. This puppy is so complex, you can read PhD and all that jazz, and it still would be black magic. It's literally classified as art, meaning sit down and start burning money. That's it. Nothing else is there. It's ludicrously complex. Like a recipe, like it has its own flow, own feel to it. And it has a ludicrously high rejection rate, even with the companies that have been like, oh, we have been doing this from what came, let's say F-16 eras. Yeah, still would have issues. So fundamentally, rejection rate is bonkersly high, because you could have a scenario where it shaked a little bit, some second nucleation site would be created, and tada, you will no longer have monocrystalline, and you have to destroy it. Destroy as in like remelt it. So fundamentally, rejection rate is bonkersly high compared to everything else, including 3D printing. It is very bad. And directional solidification is slow. And again, you want only one seed crystal to align everything, so it has to be done slow. How slow? You're basically, let's just say this is 5 centimeter. You would be pulling this puppy out millimeters an hour. Basically, like 1 millimeter, chill. 1 millimeter, chill. So it's a very slow process, like ludicrously slow, and it has to require precise thermal gradients, meaning that vacuum chamber where you are just pulling it out and slowly cooling it, like cooling from here to here could take as long as 14 hours. So that takes very precise control. And again, the barrier, that barrier sharpness can only be created if you have something lightweight like a vacuum. So precise thermal gradient, long cycle time, it takes time also. It's not like no matter how much money you have, it will still be a slow process, meaning whole turbines and everything else that is done conventionally is like mass producing it. This puppy is like, chill. We're going to deliver your order in 6 months. Like, chill. And only few places can make it, like India, China, Russia, America, Europe. And again, only in these countries, only some of them. And India just got into this, as in like in 2021, the first batch of 60 blades were created. Now, like, okay, how much jet engine with this? Well, one helicopter jet engine. One. It took us years to get this point. And yes, it is that complex. There are 200 countries. Most countries won't even try this because that's how black magic it is. And you're like, okay, we have the alloys. No, you don't. The alloy's rough composition is known. The precise mixture, no, because the polycrystalline requires certain different kinds, so grain boundary does not slip through each other. But again, if you do not have grain boundary, that metal alloy is not desirable. So you have to change it so it does not waste your precious metal volume. It's very black magic. It's almost like we tweaked this, now we have something awesome, then we tweaked it, it became garbage, we keep tweaking it. That's how it works fundamentally. And India's right now is still at like, like less than 1,000 per year, I think. Again, defense secret, so I'm pretty sure they're not going to tell me directly how much we are making, but it's not a lot. It's not a lot. So it's not like, even if you have the money, it's not like you can mass produce, fighter jets as much as you want. Because again, this is a very surprisingly serious bottleneck. Like physically, it takes a lot of time. Oh, not to mention, once you have that, you generally only have what we call internal passage in them. You do not have that tiny drill holes. So to drill those holes, you have to have EDM stage afterwards. And to make sure that EDM did not do any damage, you have to do grinding stage again. And then you have to do coating again. So there is serious limitation. Like in terms of time, like this puppy will eat money like there is no tomorrow and still will not be fast. It's like, it takes its sweet time. So there are serious limitations. People are looking for something else. So generally in future, there are certain looks, certain rumors at this point in time, is that people are looking into high entropy alloys, basically going from this puppy to this puppy. Now, the benefit of this puppy is that this has weird properties. And again, if we can manufacture it, if we can get the properties into the final product, not in like lab, but like actual product, it would be interesting. And high temperature should be allowable, meaning we should be able to cross between 1500 degrees Celsius. And again, even if the metal blade itself cannot go that high, even if let's just say it only goes to 1200 degrees Celsius, that still would be more than enough, because again, you have cooling air. At that point in time, you're like, okay, flame could easily go to 2000 degrees Celsius. So high entropy alloys. And what are those fancy puppy? Basically, you mix everything in equal proportion, like 20 into 5. So you have 20% of 5 metals. It's very, very weird. But again, in principle, this could allow next generation of technological leap, like how superalloy allows our jet engines to be like here where they are right now. This could allow us jet engine for next generation, basically going from 4G to 5G. And there is a big shift from the market where it's like, okay, single crystal, good, awesome. Mathematically, principle of science, there is nothing that can beat it. Like the end, that is how good it is. But it's not fast enough. And again, not everything needs it. Meaning if you are making a cheap drone, even a jet engine drone, you do not need single crystal blade for that. It's like that's only needed for fighter jets or things that are very high value. So in those sort of scenarios, people are like, hey, what if we use 3D printing? Now, 3D printing does bring one benefit with it, because the internal cooling path in this has to be good, like because you want the air to be flow. And again, just by changing the path geometry from the casting path, because again, casting is limited, basically how liquid metal will flow, how much it will displace the wax or plaster, whatever you have there as a negative system, it has to be like, good enough where it can flow. That limits your geometry. But when you're 3D printing, geometry becomes lol. You can have ludicrous geometry that cannot be ever flown reliably, but flown as in like, liquid metal flown into it. Yeah, that won't work. But in 3D printing, I got this. So that could give you a much better cooling performance. Now, 3D printed stuff, can that be directly used for drones, cheap drones? Maybe. But if you want to use like, jumbo jet or something like that, then you have to HIP that, hot isostatic pressing. And after that, its strength becomes what we classify as good enough, meaning General Electric, they have not been shutting up about this, that they finally figured out how to make a 3D printed part that works in a jet engine. Now, again, right now they are using it in a power plant jet engine. And if I'm not mistaken, the jet engine that is in India's aircraft carriers, they have 4 of these puppies. Yeah, 4 of those puppies. Those have 3D printed blades. And again, more and more people are switching to it, because again, if you're gonna strip it down after 20,000 hour anyway, or even 10,000 hour, the 3D printed blade has to only last that long. And if it's exponentially cheaper, which it will be, it's like shut up, take money, because HIP is far more simpler. It's not like very sensitive. It's like, oh, it has to be perfectly and you have to throw the part away. No, it's like, I got this. And 3D printing, heck, you can print large volume of it in single printer. And if you have multiple printer, you can just like ham it in, meaning you can literally have 24 blades per 24 hours. Like that can be done, or maybe even more than that. Which that's the whole point. The process of 3D printing and HIP is scalable. You can go YOLO on it. So fundamentally, and all it has to be is good enough, and HIP makes 3D printed part good enough. 3D printing makes parts with intricate geometry that makes the performance good enough. So there's a lot of effort into that. It's like, if we do not need single crystal, don't go for single crystal. And production speed matters a lot for defense, because again, right now Ukraine does not have the luxury of like, okay, we're gonna make a single crystal, then we're gonna make a jet engine, then we're gonna find a missile body to it, and then we're gonna put it and launch it. Nah, ain't got time for that. 3D print it and go. HIP is also too expensive at that point in time. So production speed matters a lot. And again, this is a very delicate system, like single crystal. So people do not like it. Like people want engineering to be like, okay, in 1970 it used to take us like 24 hours to make one blade. Now it still takes that much. Is like, what's the point? So that's why like future is looking into these 2 core categories. First, switching away from single crystal. Second, if we cannot switch away, at least switch to high entropy alloys. In principle, that could allow us to go even hotter. So this was my presentation on basically single crystal turbine blades. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me extra disappointment. Please leave a comment, because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.